Hello and welcome to today's Würth Elektronik webinar presented by our experts from Würth Elektronik and Infineon. I'm your host, Amelia Thompson, and presenting today's webinar is Jennifer Guerrero, Product Definition Engineer with Würth Elektronik, and Heiko Redinger, Product Application Engineer, Gate Driver ICs at Infineon. In today's webinar, we'll focus on the essential features and benefits of the 2EP IC. Our experts are going to share some tips and tricks on component selection, discuss supported supply topologies, and also give some practical insights on how you can avoid common design pitfalls. As a reminder, because you registered for today's webinar, you will automatically receive the recorded video and the deck provided when it becomes available after the show. This follow-up email will come from our email address webinarteam@we-online.com. That's webinarteam@we-online.com. This presentation is about an hour long with our experts answering some questions at the end. To pose a question, simply ask it in the chat box. And if you think of a question later on, or if we don't get to your question during today's presentation, we will respond after the show. So you can reply back to our email, webinarteam@we-online.com. And you can also ask those questions directly to that email, and we will get in touch with our technical experts. So sit back, relax, and enjoy today's webinar, Technical Insights into the Circuit Design and Operation of the 2EP Open Loop Transformer Driver IC, presented by Würth Elektronik and Infineon.
Yeah, thank you and welcome to this short training. My name is Heiko Redinger. I'm a product application engineer for high voltage ICs, as well as our new gate driver and power open loop transformer driver IC, what we have here. Today, we want to present the technical insights into the circuit design and the operation of the 2EP open loop transformer driver, and I will dive directly to it. What you can expect from my portion, we will look at a few key aspects, why we want to use the 2EP, how we do the component selection, what kind of supply topologies we see, and give you some operational insights so that you can understand what it's all about. And of course, we give then the chance also to our colleagues from Würth Elektronik to give you some overview on the transformer side. And in the end, we have some key takeaways and some questions for you. So, what is the 2EP and why do we want to have it? From us, as Infineon, we sell a lot of power switches and gate drivers, and we think that a complementary function for these kind of solutions is always good. So therefore, we have this slogan, every switch needs a driver. And of course, every driver then basically, especially if it's an isolated one, needs a power supply. And this is where the 2EP comes in the various size. We take the supply from the primary side of the logic, and we are using a transformer like the one from Würth Elektronik to make the isolation happening. And we have a simple rectification state to create this isolated power supply solution for gate drivers. So basically every time a customer using an isolated gate driver IC, an isolated power supply in some way is needed, and the 2EP is an IC which provides that solution. And since we basically provide everything together with our partner of Würth, we can give you the whole solution what you need for this system. So how did it look in the past? We have a legacy product, an IR2085, which was using basically external MOSFETs and a lot of circuitry around, but in the end, the rectification stage was similar. And we have then, of course, a gate driver. Now with the 2EP, you can have the same functionality as before, but with a significant reduction of bill of material and therefore also of the complexity of the layout and the area on the PCB. This really gives us the chance to further optimize customer designs and therefore save them the system costs. Also, since we have not only these fixed duty cycle like in the past with 50% or what most competitors are doing, we also have a duty cycle adjustment capability where we simplify the rectification stage, and I will mention that a few times more, to give us the advantage to create asymmetric output voltages and therefore have a very easy way to make this also for silicon carbide switches or for any other power switch out there in the market. If we look at where we would see something like that, we as Infineon say we love every application. It's equally important for us. In the end, it's the customer who decides what kind of gate driver solution they are using and then what kind of power supply requirement they might have for this gate driver solution. And therefore, the questions we always ask the customers are always the same. For example, which gate voltages do you require for your power switch? And therefore, this impacts the voltage requirement and the transfer ratio of our transformer. Then how much power do you actually need in the application? Because that's basically influencing the switching frequency and the gate charge, or at least this is how we derive it from the system. But it impacts what kind of topologies we could offer with our solution. And in the end, it's always an important question to ask is what kind of isolation is really required. Here, data sheets are sometimes a bit fuzzy because the 2EP itself is a non-isolated product. The isolation comes purely from the transformer. And this is why we have our expert with us in this presentation from Würth, who can tell us much more about these topics. So if we look into component selection, what I mentioned as a target here is that first of course, I want to convince you that you want to have the 2EP there. And therefore we have here a family of 4 variants which basically have increased complexity inside and offer then therefore also in the maximum feature set here an option which is fully configurable in many of the parameters. And you see in this table the parameters up here. We have a different kind of switching frequency for various variants. We have duty cycle adjustment. We have in some of the products, or at least in this high-end product, an adjustable overcurrent setting. And we can therefore supply different supply examples in different applications, like specifically for IGBT, silicon carbide MOSFETs, or if it's adjustable, basically it's valid for all of these application circuitries. And the idea is always works the same. We have a kind of a transfer ratio from the transformer. We have an input voltage. We might have here for the duty cycle adjustment an offset generator, which is a small capacitor here. And this allows us with a simple rectification stage to create asymmetric output voltages depending on transfer ratio and duty cycle setting, as you can see here. And depending on what variant of the product we have, it is either very simple to adjust with a pull-up resistor or pull-down resistor, as you can see here, or it can be working also with a floating pin to adjust these kind of settings, as you can see here in this table. In the end, we would also recommend the customers to start with the most configurable one and evaluate the circuit design, and if they figure out a solution which is then matched or mapped in one of our simpler products, they can basically make that solution also happen in their design, while they can easily make assembly adjustments here, which then influence the assembly cost of the final application. If we look at the parameter requirements for the transformer, I will just give a few bullet points what are important here and leave this one to Jennifer for the details. So basically everything in our circuit design have kind of impact on the output voltage because it's an open loop design, and open loop means there is no control path to the starting point which can adjust somehow the output voltages. So everything might impact our voltage drop. So for example, what we need to consider is we don't want to have saturation of a transformer, so we need to keep the voltage time product in mind. Then, of course, we want to have a leakage inductance which is properly working for us. So if you look at this equivalent circuit here, which is rather simplified, this is one which is not contributing to the transfer of the voltage, which is here in series. So this would create some losses. So by definition, we want to have it low. However, this can also impact other things. The main inductance is, of course, most important to efficiently transfer everything to the secondary side, which is therefore always a solution that we have. Bigger is better, and also it reduces the impact of the ripple current here. The winding resistance is obviously clear. This is actually a ohmic loss, which we want to minimize as best as possible. So here, this is influenced by the windings and the wire diameter in the construction of the transformer, and therefore we see it there as well. Last but not least, we have also the capacitive coupling outside. This is important for the common mode in unity, and this is very much influenced by the mechanical construction of the transformer. And of course, I already said last but not least, but we have the working voltage. I mentioned that already. This is important for the overall usability in the application, and here the parameter is the wire insulation usually, which is given also by the construction of the transformer. So with these two key elements, IC and transformer aside, we still have some passives and rectifier diodes. And also this is very important for our product to have the good selection here. In the beginning, we have here up to 3 configuration resistors, depending on which kind of part we are using. But we force our customers to use 41 specific resistor values in this discrete configuration, because these resistor values define exact parameters, and these parameters do not scale. So these are discrete values. If the customer is selecting here a different resistor value, not one matching to our E96 series value, then the product here would select the closest parameter matching to that one. But since we always have tolerances, you cannot really rely on that. You have them, for example, if you have multiple one of these ICs, that they select the same value. So it's always recommended to use a resistor value from the E96 series matching to the ones given in the datasheet to really achieve the settings you like to have. On the capacitors, it's always important to have here low ESR values, because you want to reduce the losses and you want to reduce the impact on all the systems. And of course, if we are looking here for output voltages in the range of 15 to 20 volts, you should also consider that they often have a D rating. Depending on the voltage they see, the capacitive value in itself might be lower than what is originally promoted there. For this series capacitor, what I mentioned, this is our offset generator. It compensates basically for this asymmetric voltage that we have, and also the asymmetric load. And we have this kind of estimation formula to calculate this kind of voltage given the maximum peak-to-peak voltage you want to see here over the capacitor and the switching frequency of the 2EP used. For improved startup behavior, our recommendation is, of course, to limit this value, even though the calculation might have a bigger value mentioned here. The only impact what it will happen is that then at a point you will have a higher peak-to-peak voltage ripple at the capacitor here. For the output capacitors, there is a similar formula here. It depends on the duty cycle, which is adjusted for the operation, and of course the switching frequency and the output voltage ripple you might expect in the system. For the rectifier diodes, we have here a simple peak rectification, so 2 diodes, one for the positive rail, one for the negative rail. Here, of course, the preferred parameters are low forward voltage drop, because again, we want to reduce the losses, as well as a low reverse current, because if we have a reverse current during the blocking phase, it would discharge this capacitor and would contribute to an additional voltage loss at the output. Of course, also important is the general reverse voltage rating. If we are providing here 20 volts, for example, for the supply system, we need to make sure that this is also in this range. And of course, since we have a startup behavior, charging here empty capacitors, the peak forward voltage rating is also an important one to consider, to not damage the components or make them age a bit faster than required. For the loss recovery, we also have a requirement for reverse recovery charge. This is basically the junction capacitance of these kind of diodes, where we want to make sure that if they need to switch on and switch off, basically, that this capacitor recharge is not limiting our energy we can transfer, and therefore reducing then the losses in overall the system. So these are the major components we need. Everything else is really optional. Any filtering or something like that is really not required. This is all built in. And therefore, we can go directly into the different topologies we are supporting here. If you remember the picture I showed in the beginning, where we compared it with our legacy product, the IR2085, where we made this voltage doubler topology, we can still use that one with the 50% duty cycle. It gives you still a very low BOM and a low area requirement, because the overall component count on the transformer driver side is quite low. But it has basically the same requirement that you simply have a fixed ratio between the output voltages of the positive and the negative one of 2 to 1. And of course, as always, the transfer ratio of the transformer is giving basically the output voltage here, depending on the input voltage. If we are looking at the full bridge rectification, this is where we have 4 diodes here. So every time you have a supply change, you get current flowing through 2 diodes. Therefore, you have a bit of a higher voltage drop, but this might be preferred in cases where you might want to have a single output voltage and especially a very low voltage ripple, because you basically have in every term, you have energy transfer into the capacitor here. Important to notice is also here in this solution, only a 50% duty cycle is allowed, because you need to make sure that you always have the same ratio here in the output stage. Our part especially is suited, of course, for the duty cycle adjustment, and therefore our solution, what we say, is always the peak rectification. This is what you saw also earlier on the product selection page, where this gives us really the lowest BOM area cost, because we have here even only 2 capacitors and 2 diodes for the output stage. And we just add a small capacitor, as I mentioned. This is the offset generator, and compensates also for the losses of asymmetric load. Here, the real benefit is that we can now change the output ratio from a factor of 1 to 1 to 9 to 1 to really provide a very flexible output solution, and therefore this is our suggested solution. Keeping that in mind, with that one, there are also quite many more topology options we can use, and this is basically what I want to show here. We have maybe 1 2EP, but we need many output voltages, and therefore we want to keep the overall parameters here in mind. Just as a reminder, if you have not seen in the data sheet, the product itself can provide up to 13 watts at its outputs. And this is at the IC. Then, of course, afterwards comes the transformer, the rectification, and so on. So this gives you kind of an idea what we can provide here at output power stage. And with the overcurrent limits we have at 50% duty cycle in the range of 0.58 amps for the simpler versions, and for the extended versions it's 1.1 amps, which gives you quite a lot of power here. And therefore we can not only supply a single switch, but we can use the dual output transformer to provide immediately 2 channels for the supply voltage, but we could double that up here also with a single transformer output, where we have then basically 2 separate ones. Here the benefit might be that the capacitive coupling of a single transformer does not impact directly the second channel, while in a combined transformer there might be some crosstalk here, and you would see that impact in your application. But this all depends on these capacitive coupling values, what I mentioned earlier in the selection. And we can still double this up and say even here we can provide this for a full bridge transformer if, of course, the power need per switch is low enough so that this one can supply that one. And if you go one step further, for example, if you're using an Infineon Easy module with a 6-pack inside, you could basically provide 1 IC and having 3 dual output transformers to provide something like that. And still, this doesn't stop here. We have some special cases where a customer might want to have a transformer, of course, for a positive and negative supply for the gate driver, but a second one just using the same negative voltage basically as a positive voltage for the sensor input. Could be an ADC, which is isolated and needing an output voltage. Could be another rotational sensor or something like that, which can be supplied via the same stage, just using these same transformers. Or saying, I want to have just two different output voltages, one positive, one negative, and having them with the turned over rectifier diode into two positive output voltages. All this is basically possible. The IC itself doesn't really care how this energy is distributed as long as the series capacitor is there. The symmetric approach will occur in the transformer and avoids then a saturation of this transformer stage. So how could you test something like that? For this, we have worked together with our colleagues from Würth to provide 3 evaluation boards, already in two of them fully assembled, ready to use. So I start here from the right, where we have an evaluation board with the voltage doubler topology. Here we have this transformer specifically assembled so that we can provide a dual output IGBT supply with a plus 15 minus 7.5 voltage. It operates then with 50% duty cycle and uses a transfer ratio of 1.71 to 1 to 1. It's here pre-populated, as mentioned. The second one in the middle is also fully pre-populated with optimized settings for silicon carbide supply with plus 18 minus 2.5 volts. Here we are selecting a duty cycle of 14%, meaning it's quite narrow pulse all the time. And this is why we can achieve this kind of high ratio between the positive and a negative supply voltage. And the transfer ratio of this transformer has 1.4 to 1 to 1, meaning the output here is always the one with the lower ratio. And last but not least, we have one which is a bit more flexible. Here we have a partially populated board, which then basically offers 3 different solutions for the transformer in the ratio of 1.25 to 1.4 or 1.5, always to double 1, so column 1. The outputs are always the one with the ratio 1. And we are having, as mentioned, these 3 transformer options. And of course, customers can select here with these resistors on the input and a matching duty cycle to build a transfer ratio and an output voltage which matches the application need for MOSFETs, for IGBTs, or for even gallium nitride switches, depending on what is really the requirement. And with these, I just want to close my presentation with a bit of showing what kind of parameter impact these can provide. And we use basically this evaluation board to create these kind of measurements. And the first parameter I want to talk about is the leakage inductance. I mentioned earlier that here, of course, it would be better to have a lower value because this would reduce the voltage drop. And you can clearly see this one as well here. Yeah, you see the orange color causes a bit less voltage drop at a certain output current than the green one with the higher leakage inductance. But still, as mentioned, of course, lower is better, but we want to make sure that the startup behavior is better. And you see here already, if I have a very low load current, the one with a low leakage inductance is rising very fast. So you get an over voltage at startup, while the gate driver, for example, is not having a PWM operation yet. So it's only the idle current of the gate driver which is required. And this could create an over voltage. And the customer would need to consider if this is acceptable in the application or not. If it's not acceptable, then the one with the higher leakage inductance is always better. And this is basically why we selected for the transformers we provide on the evaluation board, a one with a higher leakage inductance, because it gives us the better startup behavior so that the customer doesn't need to consider that one from the very beginning. Then, of course, I mentioned everything which causes losses like series resistance, and this includes winding plus external resistors on our circuitry. Could have an impact on the voltage drop. Here we made someone where we said, okay, 0.1 ohm or 0.57 ohm. There we have basically an external resistor parallel to one, and we see there, of course, very clearly there is a higher voltage drop at a similar output current when we use this one. So here, important message again, lower is better. If you can reduce the loop resistance in your circuit design, you will get a better performance over voltage spread. However, just keep in mind, the application usually, when it's running, is somehow drawing a constant current out of the supply, because PWM switching is usually in most applications not switching so fast or not really switching between a lower level or a high level. There are some exceptions, yes, but not most of the applications stay constant switching frequencies, and therefore you could optimize your circuitry always with the expected voltage drop and just increase the input voltage to the complete circuit, and therefore you would have still the stable output voltage on your system. And finally, of course, we can also play with the switching frequency. I know that customers tend to try to increase switching frequency as much as possible because it brings down the size of the magnetics in the system. However, please keep in mind, higher switching frequency means higher losses in all the application corners, and you see this clearly here in the voltage drop in the system. So our recommendation is being as low as possible, but you would need to consider the voltage time product to avoid running into a saturation effect of the transformer. So this is always something which needs to be decided on. And with that, I would like to hand over to Jennifer to let her tell us a bit more about transformer designs.
Thank you, Heiko, for this amazing presentation. I will now start sharing my screen. And yeah, so we can start a little bit more about the transformers. So good morning and good afternoon, everyone. Depends on where you're joining. So what I want to first talk about here will be more about, because we have different backgrounds of people who are seeing us, why we are using a gate drive transformer, what are the benefits of using it. Then also we are going to be talking a little bit more about the difference that we have in the market of some gate drive transformers, and then we can go to the core that is related to the design itself and our new family series, which we develop accordingly with our Infineon partners. So let's start with this quick overview of the key benefits. So first, we can talk about the galvanic isolation. So this is essential when you need to separate the control side from the high voltage power stage, especially in high side gate drive application. It prevents the ground loops, protects sensitivity of the circuitry, and is a must for reinforced installation, like when we were mentioning before, setups like EV, solar inverters, among other applications. Related with the power transfer, this is more about one of the specific of our types of gate drive. So, but still it applies also for the other one. But unlike digital isolators or optocouplers, which need like an extra power supply on the secondary side, the gate drive transformer can transfer both of the control signal and power together. And now, when we're talking about the negative gate bias, it's easy to implement it with the gate drive. And why it's important? Because for silicon carbides, and when we're also talking about GaN switches, this negative bias will help us to like ensure like clean, fast turn off, and also it will prevent also some unwanted effects that we have from the from, as it calls, the Miller effect. Let's say that we can say that it's a boost way or to a robustness to avoid this kind of noisy or high DVDT environments. The second one, or sorry, the fourth one is the related with more of the digital transformer, that it's about the short propagation delay, because here we need a very fast timing in this kind of connection for for having a very a good signal transmitting. And then we have, as always, for all transformers, the benefit of the voltage and the current scaling. So by adjusting the turns ratio, you can match your IC output to the gate voltage you actually need, step it up, down, whatever it needs. Yeah. But people think that we are only using gate drive transformer only for the galvanic isolation, but it also solves the problem of any high side switching. Usually when you need to have a high switch or high side switching, you have some sort like of bootstrapping capacitor or very high voltage that the driver IC may not support. So here's where the gate drive transformer solve this issue. in the previous slide, I mentioned about this kind two different of transformer or gate drive that we have. So here we're going to be seeing the key difference between the signal transformers and the power gate transformer. They may both use magnetic coupling, but their function in the system is quite different. So let's first talk with the purpose and the power level. So signal transformer are typically used for low power data transmission, usually under, let's say, 100 milliwatts. For example, you can think about Ethernet, CAN, or RS communication, in contrast with power gate drive transformer that are designed to deliver energy. So often you will see in the market from half a watt, because it depends of which IC you are using and which is the application that you're currently, to several watts. This is to actively switch the MOSFET, or in this case, the wide band devices like silicon carbide, and in other cases, also GaN switches. And another big difference now with the we're talking between signal transformer and power gate transformer is the isolation voltage. As we are more focused in the signal transformer to transfer this kind of signal in a very smooth and fast way, we don't need this kind of require of high voltage isolation. So sometimes it's up to 3 kilovolts, but this is very fine for data interface. We are now talking about the gate drive, the power gate drive transformer. They often need from 1 to 6 kilovolts or even more. It depends of the application that now we're currently using, because there are stricter standards that we have to comply. We have to have higher reinforced isolation designs. So it's a must. Now, if we want to talk a little bit different about the core, obviously it's also going to be varying depending on the application, also for the signal, but we can often generalize for signal transformer. We typically use a small ferrite cores optimized for the bandwidth. Obviously, thinking to that is always for optimizing the bandwidth of how we are transferring the signal. But in power gate drive transformer, the choice depends on multiple factors. So we are talking about the switching frequency, thermal stability, saturation behavior, as Heiko also mentioned. And this is because we need to optimize for the volt second capacity. In addition, we have to think about, as I mentioned, the low leakage and the high isolation. So because of that, we are now talking about the parasitics. Usually for signal transformer, we are trying to do minimal parasitics, especially low capacitance. This is to maintain the signal integrity. But when we are talking about the power gate drive transformer, we have to balance between the leakage inductance and capacitance to ensure this kind of fast energy delivery without compromising, let's say, EMI performance. And that make me talk about a little bit sorry about of the CMTI, but we can talk about it in the like in 4 or 5 slides. But this one is one of the most critical parameters in gate drive designs, especially for the silicon carbide based system. And for people maybe who don't know what is CMTI, this describes how well a gate drive circuit, including its transformer, can tolerate extreme fast voltage change between the primary and the secondary without, malfunction or breaking down. So in high performance converters or inverters, the switching event can easily reach into 50 to 100 kilovolts per microsecond. So when that happens, any parasite capacitance between isolated domains can act like coupling pad. And we are going to be having this displacement current across the isolation barrier and inject this noise into the control side. So when we have this, we having a CMTI very low, and this noise can cause serious problems. We have gate signal corruption, false turn on. You can go on with what are the problems that we may have and that they can impact the IC. So a tip here for the CMTI is very influencing on the winding symmetry and insulation strategy, and most important, the parasitic capacitance between the windings. So even if we're trying to reduce even 1 or 2 picofarads, it makes a difference into the CMTI. And lastly, but not less important, about the main applications and the typical concerns. As I say to you, signal transformer mostly use communication interface. Again, think CAN, RS, Ethernet. Meanwhile, for the gate drive transformer, we are using it for driving power devices, so high speed, high voltage design. So, and in signal transformer, we're focusing more over in the distortion and the signal losses. And for the gate drive transformer power, we are focusing on the shift to fast. to also the clean transition, having low EMI, and making sure that this transformer can deliver enough gate charge consistently and safely. And now you might be wondering, why do we classify this transformer as a signal transformer rather than a power transformer? It comes down to the role like it plays in this circuitry and the amount of power that it handles. So in this case, it's used like a signal carrier. So think about like a digital on-off path across isolation. And in this half-bridge gate drive, the transformer main job is to transfer the gate signal from the control side to the switching side. So not to deliver power in the conventional sense, but we're talking about more a very short pulse width and low average power, typically under 100 milliwatts per cycle. So the task here is to send the gate driver command across the isolation barrier fast and clean, while, as I mentioned before, the signal integrity. So we often call this kind of transformer, you can check it also as a pulse transformer. Its purpose is a small signal transmission with high bandwidth and tight timing. As I mentioned, this is important for having a short delay in transmission. So it's different from a power transformer, which will be designed to deliver continuous energy. Here are some of the parameters that I'm going to be talking in the couple of next slide, but it's for you to remind that these are parameters that we need to take into account when we are designing a gate drive transformer. Now, this is just another example that I wanted to showcase about a signal transformer, but here is like a double end configuration. The driver IC gates two complementary signals, and yeah, and you can act it like as a push-pull fashion way. But now we're gonna go focusing in our examples for the power gate drive transformer. So far we have covered signal gate transformer, and that was very often used back in the days, but that have changed in the couple of the last years. That is because when we have the rise of this kind of new devices for silicon carbide and integrated gate drive IC, in modern design, this signal isolation and the level shifting is now handling inside the driver IC itself. So that what means we no longer need to separate the signal transformer between the control and the gate. So, however, what we need for this IC now, it's power. And that power must still be delivered across this isolated barrier. So here's where our power gate drive transformer come into play. The diagram here shows that yeah, we need an isolated auxiliary power supply. It's typically built as a flyback, push-pull, or if in any case, any other custom transformer that we are able to provide at any time. And as you see here, now this transformer is no longer transferring the signal, but is now responsible to deliver the isolated power supply to support the gate drive circuitry. So now, in essence, we have shifted the transformer job from signal transmission to power delivery. So that is how we are evolving into the gate drive transformer, especially in the high performance silicon carbide systems. Here's just an example of where we could use our new series of Würth Elektronik auxiliary gate drive transformers. And it can be used, for example, in, let's say here, the three-phase silicon carbide motor drive system, where a silicon carbide MOSFET on the high voltage side, then these switches operates at very high speeds and require very precise gate drive voltage, usually often from as he also show plus 15 minus 7.5 or similar, but it depends of the ICU that you are also looking and the voltage that you're requiring for. But what is important to see here is that we have or we need to use isolated auxiliary power supply. This is where our gate drive transformer comes into play. And since this is a three-phase system, you typically need 6 isolated power supply. And what we are using in this isolated power supply for the transformer, here we are designing compact, optimized for low leakage inductance, and we are designing here to meet reinforced isolation and partial discharge, required for some of this safety that we have to comply into the motor control application and industries. So the key takeaway here is when we have, or even though that signal isolation is handled inside the IC, the power transformer is essential to support this high speed, high efficiency silicon carbide switching in almost most applications. Now that I have showcased and give you a little bit more background of what gate drives can be used or what they can do, now we can talk a little bit more about what was the consideration before designing a gate drive transformer. When we are designing a gate drive transformer, there are several case parameters that directly affect our system stability and long-term reliability. So first, we can talk about the leakage inductance. As Heiko mentioned, we try to want to put it as low as possible, but it's obviously going to be dependent on the system to support the fast switching. High leakage, just as a general example, high leakage leads to voltage overshoots. It depends, as again, in your system. Slower turn on and potentially uneven switching behavior between the high and the low side devices. So this is one of the critical parameters. If we go to the distribute capacitance, this one sometimes is overlooked, or I can say that most often the customers don't think too much about this capacitance, but it's very important because it occurs between the windings, and too much of this distributed capacitance can cause common mode noise, which is especially problematic in high dB/dt silicon carbide or GaN devices. So we have to manage this winding layout using take-care isolation between layers, among other techniques. But obviously, again, if we are trying to optimize this as zero as possible, it will affect other parameters. So we have to keep it into a balance. Then, if we're talking about the core material, the choice of the core material will determine your efficiency. You need a high permeability, low loss core that performs at your switching frequency. Again, depends of what is the application and the IC that you're currently using. But typically, we have seen or we have designed between 100 kilohertz and 1 megahertz. So this helps reduce the core losses and keep the transformer compact. Now, air gap. We try to reduce for the gate drive transformer, we try to reduce as much as possible having the air gaps. So why? Because a gap lowers the effectivity of the permeability, and we have to increase the number of turns. This will also introduce unwanted flux leakage. Also, when we are talking about this, make sure that there is no DC bias that could cause saturation. So it's something that we take into account. Obviously, in other kind of application or transformer, air gap is needed. So yeah, I'm just focusing on the transformer or in the gate drive that we're trying to design for these applications. So for the core size, obviously, because of high frequency and everyone wants to go to smaller and smaller, uh, this is kind of something that we would wish to have, but it can affect in different kind of electrical parameters, leakage, distributed capacitance, stuff like that, or when we are not able to accomplish all the electrical parameters that the customer needs. And nevertheless, what we're trying to do here is trying to have a core that it's big enough to wind all the turns in a single layer. Why? Because this helps to minimize the parasitics, like the leakage, as I mentioned, and the interwinding capacitance. So slightly larger cores might be needed to achieve this kind of sufficient magnetizing inductance. Now, with the winding placement, this is critical because the way that the winding are laid out, it affects everything. As I mentioned before, how we're going to be doing this kind of distributed capacitance, it also will influence the technique that we're going to be using. So sometimes we use interleave or bi-filar winding techniques to keep this coupling tight and leakage inductance low. So this is another thing that we have to take into account. And as obviously the core saturation is something that we have to avoid, that transformer must stay out of saturation at all times. This means that the volt second product or the voltage that is applied time the pulse duration must stay within the safe limits. So if the average voltage over time is not zero, you're risking here flux walk and eventually core saturation. And this is something that we don't want. And dielectric isolation. This is other thing that we have to take into account when we're trying to design transformers or gate drive transformer for these high voltage applications. Uh, they think that, or people often think, okay, we just need to comply, but most over it also requires different kind of requirements, creepage clearance, functional, basic, or reinforced, and this has a lot or take a lot of the capacity in the building of the transformer. So we need to also think into what we can do inside this small gate transformer. So also clarifying with this kind of isolation, we need to also think about how we're going to be testing or how we're going to be complying with the partial discharge. So in summary, the transformer design isn't just about, let's say, turns or voltage, but every layout or everything that you're thinking about material decision, it will influence in the final performance. And something that I think that often when we're designing or when people are designing transformer, sometimes we don't think beyond the norms. And people say, okay, let's just say we're going to be just compliant with creepage and clearance. But the real challenge sometimes, and especially in modern gate drive transformer, is meeting the partial discharge requirements under normal condition or real working conditions. So people may not know, but partial discharge or maybe PD, if people have heard like that, it refers when we are talking about some microscopic electrical discharge that will occur when, for example, we're localizing electrical field stress and it exceeds the breakdown. So we don't want that. Even thought, for example, if you see, okay, we are applying it and the gate drive or the isolation didn't break, don't think in that way, because even if the insulation as a whole hasn't failed, over time, that is why we are continuous in this profile, over time, these micro discharges degrade insulation and can lead to the catastrophic breakdown. So according to the guideline, this is just an example. For the low voltage PD testing, it's critical to test not only to the peak voltages that we have in the system, but we also have to simulate the working voltage stress over time. And in our transformers or in our Wood electronics transformer, we develop when we are trying to develop a new series like this one, we evaluate multiple insulated wires, let's say triple or whatever, but also we assess the insulation between the thickness versus the performance. We test also combinations of winding structure and insulations to identify the setup that vary are consistently for all the series to achieve the PD-free performance at the voltage that we require from our partners or from our customers. It's worth like noting that for this new series, we are not doing it with air gaps, as I mentioned before, some of the design techniques that we wanted to be implement, and that is very intentional. We have when we have gap cores, typically allows for higher DC bias handling, but they lower the effective of the permeability. That means that we're increasing the leakage and we are making harder to comply with this PD management. So instead, we keep this design on gap. You can couple the transformer to the DC blocking capacitors, making it suitable for DC bias, but ideal for high isolations. This is also what I wanted to showcase the important when it comes to silicon carbide drivers, how to manage the efficiency, the size, and the parasitic effects. So with the silicon carbide, we're dealing with very fast edges. We are talking about DVDT values of 50 to 100 kilovolts per microsecond. And this is great for performance, but it comes with challenges. So one of the big ones is the capacitive coupling. When we have a small parasitic capacitance between the high voltage and the low voltage domain, we'll start displacing this current when those edges hit. I put here an example. Let's say we have 12 picofarad between sides and we're switching at 80 kilovolts per microsecond. So that is already, if you just do approximation, it's already close to 1 amp of displacement current and just flying around there in the system. Why do we care? Because this current is going to be stressing the isolation. It will cause EMI through the cold mode currents and can actually lead to false turn on the MOSFET, which is obviously something we want to avoid. This is where the CMTI that was mentioned before comes into play. It's basically the ability of the gate drive to ignore this kind of noises or high DVDT and it still function properly. If your layout or transform injects too much common mode noise, your CMTI margin drops and your design becomes very vulnerable. Even it looks like fine paper, but it will not pass a lot of things or certifications. So based on our experience and also on the applications notes that we have published along of the years from Wood Electronic, we recommend to keep the performance stable. So try to keep the parasitic and below 10 picofarads in your isolation supply design. Use a very compact layout, short traces, tight loop. Place your output capacitor as close as possible to the silicon carbide driver. And if you can use a Kelvin source connection to separate the switching current from the gate sense pad, that will help to reduce the gate ringing and keeps your signal clean. So bottom line, if you want to ensure reliability in the high performance silicon carbide system, Controlling the parasitic isn't optional, is one of the most critical aspects of the gate drive designs. And now the focus of this my presentation is to showcase you the overview of the latest edition of our auxiliary gate drive transformer family, designed specifically to support today high performance gate driver IC. In this table, you can see all the different parameters and how they are tailored for our specific IC from our partners, Infineon to EP1 from the new ICs, and from the older family that it was IR 2085. So yeah, and we have optimized these parts from different trans ratio, ranging from 1, 1.07, all the way to 1.4. Even if, for example, if you see something here that it doesn't okay, you need a different kind of trans ratio, we're able to support because we also do customized solutions towards that. We also display here the leakage inductance has been kept intentionally low between 0.35 and 2.28. Again, it depends also on the application, what you want or what you are going to prioritize to support the fast switching with minimal delay or ringing. We also provide here the unipolar second here, which is the key indicator of how long and how hard the transformer can drive without risk of the saturation. One of the most important improvements is in this new family series. It's also the interwinding capacitance. As I mentioned before, we have to do it as low as possible. I think that it was as low as possible from 1.6. I think that it was lower for all the custom transformers that we did, but we are able to provide different kind of solutions. And again, this is a huge benefit for the CMTI, EMI performance. And so, yeah, here in the right, you see the mechanical outline. So these are very compact SMT, all under 20, 15 millimeters, height under 10 millimeters. It's very ideal for different layouts. And of course, it's very the standard part that it will require or like it match any requirement that you need. We can also customize or develop fully customized versions if, for example, as I mentioned, there is no specific electrical or mechanical or safety targets that you may see here, but we are whatever is needed, we will be able to support into this new custom solution. And now let's take a look at the core of this presentation, our Würth Elektronik auxiliary gate drive transformer reinforced with high voltage dual output transformer series. So this series is designed for dual output gate drive applications with bipolar voltage for each output. I already say to you, example 15 minus 7.5, but there is a lot of different of outputs that we did. And this series meets reinforced isolation standards according to the IEC 618 and the 62368. So also we have complied with the creepage between 16 millimeters and also in between the two outputs, so they're isolated between them, so they can be there's a full separation even in their high voltage stress. These parts, when we were testing it, we tested up to 12 kilovolts surge voltage and achieved the partial discharge that I was mentioned before below the 10 picocoulombs. So both at inception or extinction. So this is exceeding most of the industry specs requirements. So it can be used in almost every application. As far for topology, this series support both half bridge open loop, full bridge open loop, with our using the IC of the ER2085, but most over with the new family Infineon series that is the 2EP. You can already find these multiple reference designs online using this transformer, both from Würth and from our Infineon partner web page. So anytime, just Google it and you will find it as the first solution in your web search. What makes this series very standing out is that, as I mentioned, bipolar output support for high performance gate drive. Temperature wise is also very low profile, ideal for compact designs, full SMD compatibility with pick and place, real packaging, and most important is standard catalog availability. So anytime that you need something very fast, it can be delivered up to 48 hours. So it's going to be off the shelf. Electrical strength. So, as I mentioned, low interwinding capacity for CMT resilience, high volt second rating to avoid saturation, and multiple trans radio to fit various IC and bias configuration. So in terms of safety, we also support reinforced isolation, high cryptage and clearance distance, full certification of ROHS and REACH compliance, and soon we're also going to be compliant with all the ACQ200 qualification for the transformers. So this going to be making a very huge difference for industry's qualifications. Now that I have finished my presentation, I would like to send back to Heiko so he can do the takeaways.
Sounds good. Give me a second. Okay, yeah, thank you, Jennifer, again for this impressive information about all these transformer details. And I just want to close basically with the key takeaways. I already mentioned that basically isolated gate driver supplies are used in basically all applications we see out there, always depending on customer designs. And of course, what kind of power switch operating conditions are used there. So what we saw in these presentations is really that the proper component selection is key for open loop gate driver supply designs, especially on the transformer, because of all these parameters we need to consider. With the 2EP together, we can offer them a flexible but easy to configure solution, which comes in with a lot of protection features I have not directly mentioned in this presentation, but if you look into the data sheet, you find all these security functions we have inside, and it offers a very low BOM per channel material cost in the system. So as a closing statement, every switch needs a driver and every driver IC needs a power supply. So Infineon has you covered, and together with our partner from Würth, you get a full matching solution for these products and application scenarios. With that, I would like to return with the question and answer sessions. Thank you.
And thank you everyone for joining our presentation. Right now, we are going to head on over to the Q&A sessions. If you have any questions, please feel free to write them in the chat, and hopefully we do get to them. Now, as a reminder, if we do not get to your question today, you can write us a question later on. If it is in the chat, we will be replying directly after the webinar. We'll get you in touch with our technical experts. Or if you think of one later, please feel free to reply to our follow-up email, and that will be coming from webinar-team@we-online.com. That again is webinar team@we-online.com. So looking at our questions, we do have some that came in prior to the webinar. First question here: how does the 2EP reduce the bill of materials?
Yeah, I think I take that one. It's quite simple. If you remember one of the earliest slides I had where I was comparing our legacy product with the new ones, you already saw there that we quite reduced here the bill of material because we integrated these integrated MOSFET switches for driving then the transformer. And this is basically the main takeaway, what you can reduce your BOM here, just to reduce the component count on the system.
Thank you very much, Heiko. Our second question here, I believe, is actually about the transformers. How can gate drive transformers be used with duty cycles above 50% or even below that? Or are they limited to symmetrical signals?
I think that I can answer that. Obviously, yes, obviously it will be depend on the application or the design that you want require, but you can do it for use it above 50 or not just below. Here the important thing is that the transformer is AC coupled, usually by adding some blocking capacitors. Like that, you are trying to maintain a good volt second balance across the core over time. So this is one of the main things that you need to consider. To do that, usually people say like, okay, just really small capacitor, but no, try to have it like a really nice proper size, because like that the core can reset fast enough, and especially when we have duty cycles that are changing. So this is something that most that you need to think about. And when you go by this route, also you need to watch out about the LC resonance between the magnetizing inductance and the coupling capacitors. That can be very tricky to manage, but it's very doable. So with a proper design, but this is one of the things that I can tell you. Just obviously you can use it above or below, but it depends also on what are the parameters that you need to take into account.
Thank you, Jennifer. This next question actually was a common theme for today's webinar, but why are there only two frequency and duty cycle settings in the 2EP100R and 2EP101R?
Yeah, that's easy. We basically make kind of custom versions of this IC where we say, okay, customers want sometimes even reduce the complexity in assembly. And therefore, we have these two variants where we don't require an external resistor to configure frequency or duty cycle, but we are using a so-called function called pin strapping. You find a lot of information there on the data sheet of this product, where we basically leave either the pin floating or tie it to ground, and therefore select either one of these two settings which are available for these individual products. While the 2EP100 is dedicated for applications like IGBTs, either using the voltage doubler topology or the peak rectification with 33% duty cycle. The other one is basically then for example, silicon carbide MOSFET applications.
Thank you very much for that explanation. Going on to our next question, we do have time for a few more. We are past our 1 hour mark, but that's not a problem. If you do need to leave to get to another meeting or anything, you will be receiving the full recorded presentation, including the Q&A session in that follow-up email. And our next question here, how does interwinding capacitance affect CMTI?
I think that I already have mentioned it when I was explaining the webinar, but you know that the interwinding capacitance is the parasitic between the primary and the secondary. So this becomes a very big deal when you are working with this kind of fast switching devices like silicon carbide or GaN. I think this is another question that what would be the ideal, I think, the CMTI for this kind of switches, but let's say 100 kilovolts per microsecond or above, literally 150 also, it will be kind of okay. But again, it all depends of the switch that you're going to be using for your application. In these cases, when we have this kind of let's say 100 kilovolts per microsecond tracing on the power side, the capacitance forms this path in the common mode current and it will jump to your control side. So this is what kills your CMTI and will makes it very, very lower. And this can cause, or it will inject the noise where you really don't need to want it. And things that, for example, what we, or well, sometimes when we are designing for transformers and people who are doing the design for the transformer, they have some techniques for, like, for example, increasing the physical distance between the windings, or they're trying to measure in different kind of insulation wires so we can try to avoid or increase this affecting of the CMTI, because like that also we are trying to increase this parameter that you were asking for. Nevertheless, is complicated because also you're going to be affecting other parameters. So it's always a depend or a balance in between. So just bottom line, faster that you have your DVDT, the more parasitic capacitance. So in high CMTI applications, you really need to take into account is the CP control, and the top priority is the transformer design. So this is the only advice that I can say for you in regards to why interwinding capacitance affect the CMTI.
Thank you for the explanation. This next question here, is reinforced insulation always needed?
Oh, not always. It really depends on the application and the safety requirements. If your design, obviously it is for something related like EV powertrain, industrial drive, or for example medical devices, you're probably going to need this kind of reinforced insulation basically anywhere that you need to protect the users from any like hazardous voltages or very high kind of power. Even in faulty condition, it has to work and it has to be safe. So maybe more contained system, something that is very isolated inside, that it will never touch the user, you can get away by using basic or functional insulation. But definitely the trend is towards to use majority of the time is reinforced insulation by default. It's easy, it's always going to be simplifying the global certification, and it supports higher voltage. The application engineer, the people who is going to be designing the PCB, can maybe use this transformer and don't worry too much about if they want to use in another kind of board with different kind of electrical parameters, that it will cause any harm to the user. So yeah, often now we're seeing more trends that everything wants to be to roof for insulation. So yeah.
Thank you very much. A few more questions have come in. So what happens if the adjustment resistor does not match the distinct value required for a specific setting? Does the IC interpolate? I think this question may go for Heiko. Heiko, are you available?
Oh, I'm
Oh,
sorry. It seems I
it's
was
okay.
somehow on mute.
Not a problem.
I just noticed basically that one. Yeah, the values are not linear interpolating between 2 points. It's a discrete value, and the IC selects the one which is closest to the matching one in our data sheets. But it is not reliably to be selected like this, because there are always some tolerances, and the best results always come with an exact match from the E96 series, as mentioned in the presentation.
Thank you very much. Our next question here: why is leakage inductance so critical in power gate transformers?
Well, it also again is it's let's say that it also will depend on what kind of parameter you're prioritizing, but leakage inductance acts like a speed limiter in your gate drive path. So the higher the leakage that you're going to be having, you were going to be having the slower gate to the charge, and that discharge of itself, and that means in other ways that you are slowing the switching. So you are going to be also having more switching losses. You are going to be having sometimes this kind of ringing or voltage overshoot that you don't want to have, especially if there is a resonance with the gate capacitance or PCB layout. So yeah, it's a little bit more complicated because in some other topologies you want to optimize and having this leakage inductance for optimizing or trying to gain less of the bill of material, but there's a way like another kind of application. But nevertheless, the majority of the cases we're trying to keep it low. It's very important. You want to clean, very efficient, and you want it to be really reliable for the switching, especially when you're dealing with these kind of silicon carbides switches or GaN in general.
And just so we can get this on record, how does that leakage inductance influence the startup behavior?
Yeah, maybe I take that one. In that case, from the IC, it's not only the transformer which basically impacts that one, but it's also the surrounding components we have on the circuitry. So you need to consider that the 2EP itself has basically output stages which are MOSFET based, and we have also rectification stage afterwards on the secondary side, which have internal capacitances. And low leakage inductance basically translates into a very fast current rise when we transition in our hard switching topology here. And this basically means that if there is no load on the output side or only limited load, that this will result in this voltage overshoot, what I showed in one of these comparison slides. And this basically is the startup behavior, what I mentioned here, that it impacts that application portion. And therefore, yeah, either we have always a good base load on the system, or we have a kind of higher leakage inductance to reduce basically the impact of this voltage overshoot at light load. We have this chapter also in the data sheet of our product. But again, it's not only because of the transformer, it's not only because of the switch, it has basically an impact of all the surrounding components required for such a power supply, and it basically impacts all open loop solutions out there.
Thank you very much for that explanation. We're going to go ahead and finish up with this one last question. I know that quite a few more have come in, but have no worries. We will be answering them later on after the Q&A session. Be on the lookout. Again, if you have any questions, you can reply directly to our follow-up email from webinarteam@we-online.com. Our final question for today, if you needed more output power than just one 2EP IC then that it can provide, and you needed 2 or more 2EP ICs, is there an easy way to actually synchronize the switching frequency between these multiple ICs? So for example, can you connect the frequency pin? It looks like the frequency pin might be an input.
I see that question in the chat. Yes, this is a rather important one. Personally, we would not recommend such a kind of an operating condition because, as it is mentioned here, synchronization is always a challenge, especially since both ICs would basically perform their own startup behavior and therefore would interfere with each other. So a solution which could be taking place is to combine basically the outputs of these power stages together, which would also, of course, require to have individual transformers for each of the 2 EPs. And therefore, since there are basically with the rectification diodes always a decoupling available, this would not interfere with the full operation and therefore would neglect every synchronization need. In terms of this frequency pin, what we have here, that pin is only for a bypass mode. But again, this bypass mode only refers to the normal operating mode, not for the startup behavior. The startup behavior is always running independent and therefore cannot be synchronized. So I need to highlight, don't switch the outputs in parallel of the 2 EP. This needs to be done at the output stage of the secondary side of the transformer.
Thank you very much for your explanation. And thank you both for presenting today's webinar. I appreciate it greatly.
You're welcome.
Thank you.
This does conclude today's webinar. Thank you again to Jennifer and Hiko for presenting, and thank you for everybody for your support and also your questions. Now, again, if your question did not get answered today, or if you think of one a little bit later, I encourage you to reply to our follow-up email. It's going to come in the next week or so from webinarteam@we-online.com. Now, that email will also include the video on demand and the deck to download as a PDF. And then if you scroll to the bottom of the email, you can register for our next upcoming webinar. It is next week on May 28th. That presentation will be an introduction and application of the SPE and Poodle board. That's single pair Ethernet and power over data line. You can also continue learning with the Würth Elektronik What's Up podcast, where we are discussing the latest and greatest in board design and component development with our own technical experts and then other leaders in the industry. You can listen to the What's Up podcast on our website at www.we-online.com/podcast and on all major streaming platforms, including Spotify, iTunes, Pandora, SiriusXM, and so much more. Thank you for listening to today's Würth Elektronik webinar. Joining us was Infineon, and I hope to see you soon.